right, today we're going to be talking about sound. Sound is a fairly short and easy lesson, just following up on waves. There's a couple of things that are specific to sound that we didn't cover on waves. A lot of the things are going to look somewhat similar, but just have a slightly different take on them. So when we get started with sound, first we want to talk about what kind of wave sound is. Sound is a longitudinal wave. So a longitudinal wave is a wave that propagates in the direction of motion that is parallel to how it's moving. So it has high pressure and low pressure areas. Looks like I'm just making a bunch of dots here, and I am. But these represent different high pressure and different low pressure areas. This is how sound moves across the room. So it's creating high pressure in terms of the kinetic energy, the velocity of these little air molecules as they transfer energy straight down the line to the next one. So this little guy right here transfers it to the next guy, and it moves through an area of high or low pressure as it goes from the source to the observer. It's a longitudinal wave. All right, the speed of sound. The speed of sound is about 340 meters per second. Sometimes it's 330. It actually depends on the temperature of the air and the composition of the air. Luckily for us, it's mostly nitrogen, a good enough oxygen to breathe, and some other inert gases in there. But because of our composition and the density of the atmosphere around ground level, the velocity of the sound is typically around 340 meters per second. So if it takes thunder 9 seconds to be heard after lightning is seen, how far away is the thunder strike? Well, velocity equals distance divided by time. What am I looking to solve for? I'm looking to solve for distance. So 340 meters per second times 9 seconds gives me 3,060 meters away. How fast does the light travel in that same time? Well, light travels a little bit faster, 3 times 10 to the 8 meters per second. So it actually takes light only 1 microsecond to reach your eye. So we're just going to forget about that in terms of the difference in 9 seconds. And we're going to say that the lightning is actually 3,060 meters away. So that's about 2 miles. So it turns out for every about 4.5 seconds is equal to 1 mile. So if you see lightning, you count for 4 seconds, it's about 1 mile away. All right, what's your range of hearing? What frequencies can you as a human hear? Your range starts at infrasonic, and that's anything. So infrasonic is anything below 20 hertz. And this is where you can start to hear certain frequencies. Typically, it's about 100 hertz where you can start to actually feel like, oh yeah, hey, I hear that one. Ultrasonic is anything over 20,000 hertz. This is where you finish. Old people, like your parents and your teachers, they can't hear that high. Most adults fade out somewhere around 16,000 hertz. As you get older, your higher frequency range starts to be diminished. It's just the way it is. So young people, keep listening to your loud music, and soon you will join us in the lower end frequency range as well. All right, so here's the thing that kind of looks similar and also dissimilar in terms of waves and sound. It works the same, but now for sound, most of the instruments that we use are going to be open-ended on one end and closed-ended on the other. So we have a new set of harmonics in terms of solving for the wavelength. So right here is the first harmonic, which we just drew on, labeled as A. So in the first harmonic, what's happening is I only have a quarter of a wavelength in the harmonic tube itself. It is bound on the closed end by a node. But over here in the open end, I can only hear sound when I hear a crest or a trough. So it has to be an antinode that reaches the opened end of the tube. So for this reason, it starts off with a fourth of a wavelength. And then every successive harmonic, you have to add another half wavelength. So for open-ended, closed-ended tubes, we only have odd numbered harmonics. So it's the first, the third, fifth, and continuing up. For these particular ones, our equation is wavelength is equal to 4 divided by the harmonic number times the length of the tube. The difference was that 4 used to be a 2 because you started off on 1, 2, 3, 4, and every other harmonic was a half a wavelength. The reason we start with 4 is that there's only a quarter of a wavelength in the first harmonic for an open-end, closed-ended tube. So we have to use this equation when dealing with these specific type of tubes for sound. And this is specific to sound, as you can only hear it when it's at an open end and you have a crest or a trough. All right, what's the frequency of an open-ended, closed-ended tube that's 1.75 meters long, vibrating in the third harmonic? All right, third harmonic. Closed end has to be an antinode at the opened end. So here, I have to solve for lambda first. Lambda is equal to 4 divided by the harmonic number, which is the third. So 4/3 times the length of the tube. And the length of the tube winds up being 1.75. So 4/3 is 2.33333 times 1.75. Not rounding any particular sig figs. Oh, actually, your answer is 2.33333. So 4/3 is 1.33 times 1.75 is about 2.3 repeating. So, and in order to solve for frequency, velocity equals wavelength times frequency. So velocity over wavelength. So we have 340 divided by 2.33333 gives you about 148 hertz. 148, 145, somewhere around that range. So that's how you solve for the frequency. All right, so that's it for our first video.